Hello again. Welcome to Chapter 10, Section 6, where we're going to talk about how we extend the cosmic distance scale out a little bit farther. So we're going to explain how knowledge of a star's spectroscopic properties can lead to an estimate of distance. And then I'm not exactly sure where the next break off is, whether we're going to get to Learning Objective 7 or not, but explain how stellar masses are measured and how mass is related to other stellar properties. We might do that in the next video or this one. Yeah. Okay, keep going. Our vocabulary for this section, we're going to talk about luminosity class. And then once again, explain how the knowledge of a star's spectroscopic properties can lead to an estimate of its distance. All right, so spectroscopic parallax. It has nothing to do with regular parallax, but it does use spectroscopy to find the distance to a star. So here's the process. Measure the star's apparent magnitude and spectral class. So we figure out how bright the star is, and if it's in be a fine girl, kiss me, all those letters. Then we use the spectral class to estimate the luminosity. All right, so we find it on the HR diagram and then apply the inverse square law to find distance. So the spectroscopic parallax can extend the cosmic distance scale to several thousand parsecs. So here at Earth, we have radar imaging that we can use. Then, I'm using the mouse. Oh my gosh. Boy, I have a pointer for a reason. Okay, so we use radar imaging to find things that are close to Earth and measure distances. So we did radar imaging to find out the distance to Venus, which allowed us to calculate the rest of the distances within the solar system. Then we use stellar parallax. I'm always laughing at myself because, yeah. Okay, we use stellar parallax to go out to about 200 parsecs, and then we use spectroscopic parallax to go out to about 10,000 parsecs. So a useful analogy is to light's dependence on distance is a traffic light that is distant and dim, or one that is close and bright. And we've kind of talked about that with our fires on a mountaintop. So spectroscopic parallax calculation can be misleading if the star is not on the main sequence, like a red giant or a white dwarf. So the width of the spectral lines can be used to define luminosity classes because the width tells us the pressure and hence the density in the atmosphere. So if you look at this right here, we have the same sort of peaks or absorption lines, but see how these are much wider. So here we have our different classes. So stellar luminosity classes, there we go with our bright supergiants, bright giants, giants, subgiants, and main sequence stars. And if you look here, those were all the ranges are. So class 1A, class 1B, class 2, class C, class 4, and then class 5. So those are our luminosity classes that we have shown over here, and this is where they show up on the HR diagram. So in this way, giants and supergiants can be distinguished from main sequence stars. So knowing the luminosity class helps us determine the distance to the star, as we said. So here we have our surface temperatures, but then we have our solar luminosities and then our solar radii. Right, so this one, the surface temperatures are all relatively the same, but the luminosities are very different, as are the size, which gives us our main sequence star or our red giants. I know it can be kind of confusing. I don't think the questions that I give you, which I haven't decided on yet, but anyway, it's just, now you've heard it. It's confusing. It's complicated. Let's move on. All right. So, and look, we're at the learning objective. So explain how knowledge of a star's spectroscopic properties can lead to an estimate of its distance. So if a star is on the main sequence, the spectral type allows us to determine the luminosity, and from the luminosity, we can figure out the distance. Now, this is the weird part that we didn't really talk about before. So if you look at sort of the main sequence and how it's lined up here, we can figure out the type of star it is, which leads us to the luminosity, right? So here is the temperature, which we can, which we've already determined that you can get from the spectrum of the star. That was hard for me to say. We figure out the luminosity. Now, right, the luminosity, if we have a high luminosity and we're very far from Earth, but we know the luminosity, right? So we know it's a super, super bright star. We know it's a bright star because it's up here on the top where luminosity is high, but it's very, 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 very far from Earth. So since we know the luminosity, we now have an equation where we can calculate what this distance is. All right, because we know the luminosity of that star. If we remember the apparent brightness, because it's so far away, it's going to look dim, but because we are able to figure out all this information, even though it looks dim, right? It could look really, really tiny because it's so far away, but now we know the luminosity and that allows us to figure out the distance. That's all that you need to know. We can figure out the distance using math. Yay, math. Go math. All right. Once again, wash your hands. Stay away from people. Stay healthy.